Hello. How's everyone? Oh, Hi, hi, Carlos.
Hello Santiago, how are you doing?
Hi, good. Good, good, good. All right, let me start by sharing the agenda for today and also an announcement. So, today we will discuss about LoRa, which is Appendix E, and Taha will help us with that. And if there's time, also we will start the discussion about DPO, and this Michael will lead it, will help us. The idea is as well to continue the discussion about what to read next after the session today. I will leave a poll on Discord where we can vote and um, perhaps if people can still add books in the comments. But basically, we will have in the poll the books that people have suggested in the previous sessions. So yeah, and one exciting announcement is that I was talking to Sebastian last week. Well, this week, last week, and we're gonna do a session. He's gonna join one of our calls. We will have do a ask me everything, anything, ask me anything session. Um, he can join us on a Tuesday, not on a Sunday. So hopefully, people can still join. And a Tuesday at 9 a.m. Central Time, which is 3 p.m. UTC, if I'm not wrong. So yeah, pretty cool to have Sebastian. So yeah, I will still announce it on the on Discord, and maybe even encourage you to come prepared like with questions. So ask the questions on Discord are ready in case you can join. So still your question can be asked, but the idea is that you yourself ask the question to Sebastian on the call. But yeah, any questions? I see some comments. No, there are not comments. There are AA note takers. Okay, nice. Uh, maybe let me check if Taha is here. Yeah, Taha, how are you?
Hi Santiago, I'm fine. How are you?
Oh, good. Thank you. Yeah, that's all I
So,
had to share. So go ahead.
let us begin. It will be not a very long lecture, but just a high level overview of what low rank adapters
Hmm. I
are
don't.
and how we can relate it with. We have some practices in deep learning. How we can relate it with basically transfer learning. Is my voice clear?
Yes, most of the time. Just it got for a second, but yeah.
Okay, cool. So. Just let me share my screen. So,
Mhm.
uh, is the screen visible?
Yeah, maybe you can zoom a little bit, just to 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 be able to read.
Yeah. I'll just explain the high-level overview of what LoRa is and how we can relate it before LoRa, like how we used to fine tune before LoRa and how we are fine tuning with the help of LoRa. These two diagrams will let us have a high level overview. So to begin with, before low rank adapters, what we used to do for fine tuning a traditional large language model was that we used to fine tune the entire weights of the model. Like if we have some downstream task like classification or maybe uh, fine tuning for name entity recognition or any traditional NLP task, what we used to do is we used to get a new data set on which we had to maybe uh, fine tune our model for that certain downstream task. So that data set was our input X. So moving forward into the architecture, we see here W. These are the pre-trained weights of the large language models. Like the pre-trained weights, traditionally, uh, they were also updated, but most of the times, like when we used to go to the while fine tuning the model traditionally, when we used to go towards the forward pass and then the back propagation used to happen, it was more compute expensive and intensive. Why? Because we were updating the entire weights of the model in the entire process of fine tuning. So as you can see here, W delta W is the update. The update we do into the original weights throughout the forward process and back propagation involved in the fine tuning. So, like this process, as compared to the low rank adapters, was more compute intensive, and for a person like me or anyone who has no access to very high end computers, it was very difficult to fine tune a large language model because we were almost retraining all of the weights of the model, obviously, which was not very efficient, and the process was not very democratic. Like a lot of people were not having access to this fine tuning techniques for their downstream tasks. So what in the paper of LoRa, what they updated, they basically added two low rank matrices rather than having the same rank updates in the large language model. We are adding two small rank matrices. They can have rank very smaller as compared to the original dimension of the our deep neural network. For example, if during the training process our dimension of the matrices is 4096 by 4096, we do not want to update those 4096 by 4096 matrices. What we can do, and according to research, what we found was that even smaller changes that we apply during the post training, during fine tuning, they can also extract the semantics of the changes that we want to have. So basically, what the paper proposed, that rather than changing the entire delta W, we incorporate two small weight matrices of dimensions R into D and D into R. Now D is the same dimension that we had during training. Like if we had 1024, 4096, that remains same. But rank is the rank of the LoRa. This rank tells us that how, like if we move the rank to a higher number like 32, 64, 128, this will be more compute intensive, and the fine tuning will take more time. And like we can say that the accuracy can be also better in some cases, but it's not always the case. But this was the proposition by the paper, that instead of updating the entire delta W, we add two small weight matrices of rank D into R and R into D. Now D remains same as discussed earlier, and R is the most important part of low rank adaptation. If you have fine-tuned some sort of a stable diffusion model, or using the high-level stable diffusion dream booth, that there is a UI for fine-tuning stable diffusion. There is a parameter of LoRa rank, like you have to enter that parameter. So that parameter is the most basic parameter of this fine tuning, which tells us like what will be the rank of the attaching to our original weights after fine tuning. So over here, this like the input remains the same, but we are not updating the entire delta W, but we are updating two smaller weight matrices. And then after the forward pass is done, we are just updating WX plus this small weight matrix. We are not updating the entire 4096 by 4096, but now the matrix will be 4096 by 16. So this will help us in maybe obviously uh, having lesser compute and having the ability to fine tune this model. So this was the major change. Like this, we can also relate to transfer learning. If you have previously fine tuned some convolutional neural network for your downstream task, we know that we used to basically freeze the initial weights of that model. Like if we use ResNet, some sort of VGGNet, some sort of convolutional neural network for any of our image segmentation or something like that, we used to keep the initial weights constant, and we just used to change a few last layers of the model to maybe fine tune or use them for our downstream task. So covering a few parameters that we can see in our fine-tuning tasks using LoRa or quantized LoRa. So as discussed, R is the rank of the matrices that we will be using. It controls the size of update matrices A and B. So lower are few parameters, but potentially less expressive. So there is a chance that if you increase LoRa rank to maybe 16, 32, 64, even 128, the fine-tuned model may learn more, very focused or focused semantics of the fine-tuning that we want to do. So it is a trade-off between model size and performance, obviously. Then another parameter that we have to input in the target modules is target model in the attention part of our large language model that we want to update during the fine tuning. Common targets remain the query matrix, the key matrix, the value matrix, and another is the output matrix. Now, our book, I believe we do not have discussed the output matrix because in GPT-2 architecture, this was not there. But this matrix was introduced in GPT-3, and for moving onwards in the Llama architecture, we see this matrix. This is an additional matrix in the attention mechanism. What it does is basically combines all of the outputs from query key value, and it transforms that all of the outputs into a single vector so that it can be sent to the feed for forward neural network. So this was not discussed in the book, the output matrix, but it was implemented GPT-3 and onwards. Okay, so moving forward, we can also include feed forward neural layers. They can include gate, this layer, gate layer, the up projection and the down projection. Basically, the task of the gate projection is after the attention layer, we focus on a few of the it filters out the information that is not required and only keeps the information that should be sent into the next layer. So this is some sort of filtering, or as the name suggests, it is a gate for only to send the relative I would say uh, 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 knowledge, or the relative learning that we want to move forward to the next layer of the model. So moving forward, the up projection, it basically increases the dimensions of the matrices to a higher dimension. Maybe from 4096 we can increase the dimension so that the model has like we can up project it upwards so that we have a better learning or understanding, and then we use the down projection to further like reduce the dimension just to distill the model and see and so that it can move forward to the next layers of the process. So it can have more targets, but the common parameters are these that are discussed. Then moving forward, we have LoRa alpha, which is basically the scaling factor for LoRa updates. Like it controls the magnitude that we are updating over here. Like it will tell us like how much scale of the weight updates we need to do during each forward and back propagation pass. So it also affects the learning of the fine tuning. So I believe these two, LoRa rank and LoRa alpha, are very important parameters when you are fine tuning a language model, or maybe a vision transformer, or maybe a stable diffusion or flux model. So then we have bias. This is just to tell whether we want to update the bias in the neural network or not. And it has usually three parameters in Hugging Face, which is none. That is, you do not want to train the bias in the matrices in the deep neural network, or all, or you want to train all of the update all of the biases, or number three is LoRa only, that you want to only update the LoRa related bias in the deep neural network. Finally, another important parameter is rank stabilized LoRa. What we do here is in the LoRa alpha, if this is true, we will use alpha divided by square root of rank. Like what it does is basically it more stabilizes the updates that we are doing over here. Like the updates we are doing into a neural network, if we use rank stabilized LoRa, it will even make the updates, I would say, smaller, as it is using the square root of r rather than using the actual rank of the model. So it can improve the stability for some tasks, like if the tasks are more complex, you can use this. But it's for as off. So if we move to the Hugging Face page, that basically has a lot of, I would say, information, and it is a very good article related to low rank adapters. So if we read a few lines, to make fine tuning more efficient, LoRa's approach is to represent the weight updates with two smaller matrices, which is called A and B matrix, through low rank decomposition. These new matrices can be trained to adapt to the new data while keeping the overall changes very low. Like as compared to the original fine tuning, these two smaller rank matrices will make the change, the weights that we have to change into our LLM or any other model, very small as compared to the normal fine tuning. The original weight matrices remain frozen. Maybe I should zoom in a little bit. So the original weight matrices remain frozen and don't receive any further adjustment to produce the final both the original and the adapted weights are combined. Like if you see a few fine-tuned model AI, you have several AI, what you can use
Sorry, Taha, the quality here in the audio is
is
not
that you can
the
just
best.
and if you models for you have it.
Hi,
Hello,
hi. Yeah, we can hear you again. No, the quality of the last sentence that you were
can
saying wasn't audible.
okay. Is my voice good now?
Now it is, yeah.
Okay. So uh, so I was discussing that another benefit of low rank adapters is that you can attach these updated weights to any of the base models. Like if we have made a fine tuning of Llama 3.1, we have those adapted weights, and we can attach those weights to a base model, like a basic stable diffusion model. Now you can choose any of those LoRa fine-tuned models and attach it to a base model. And like these weights are basically also detachable.
I have a question here. Can you hear me? Can you hear me, Taha?
So this okay. Any question?
Yes, I have a question. Can you hear me?
Yeah.
Yeah. I did some fine tuning for exactly for this model Llama 3.1, and I fine tuned this model with some specific IT data. And when I tested the fine tuned Llama model, I expected not to see anything from the previous pre-training. Like he is mentioned here that the original pre-trained weights are kept frozen. So when I asked, for example, so the model which I trained was fine-tuned with say technical data, very specific technical data. And then when I asked the model who won the football championship 4 years ago, the model still knew it. So here my question is, I don't know if you had the same experience, but here my question: what exactly does it mean that the pre-trained weights are kept frozen?
Okay. So what I understand is that, someone can correct me if I'm wrong, like the pre-trained weights are kept frozen, but we only train the newer like the A and B matrices, and like the model will not totally forget its previous training. There is also a phenomenon known as catastrophic forgetting. Like when we fine tune the whole of the model, there is a chance that the large language model can forget a few of its pre-trained data. But in this case, in LoRa, we keep the basic weights of the model frozen. We only attach the new trainable weights to the model. What it does is that the model will surely have all of its knowledge in the pre-training. It won't forget anything from the pre-training, but it will also be like more streamlined onto your case. If I fine-tune GPT-3 onto a classification task, it won't happen that it will start to forget what it was pre-trained on. It will have that in its weights, but it will be more fine-tuned on that downstream task to which we retrain the model.
Yeah, this is also my impression that basically the model still has the old capability, and you add an additional specialized layer. But exactly what this frozen means, maybe I will ask Sebastian in February, because it's not clear what does it mean in practical terms. What does it mean? Frozen.
In practical terms, it means, like, let's say your model has 100 parameters. You just don't modify them. You just don't modify the base ones, and you are gonna modify the ones from these 2 A and B matrices only,
Yeah,
but the
I get
base
it.
ones no.
I get it. But what are the implications in the behavior of the model? The model should remember or should be available to respond to the original data he was trained with, or he should know only the latest data he was fine-tuned for the downstream task.
Intuitively, yeah, I would say it should, like, unless the LoRa matrices are very big, then unless that's the case, the main capabilities of the model will still remain, because they're the ones that have the biggest presence on the model. Like if you have a model with a billion parameters and your LoRa matrices are only, I don't know, 10,000, you are just changing 10,000 of those billion. Like you're just adding new knowledge on from those 10,000. So the original capabilities will still be there. In That's how I intuitively think. But yeah, that's a good question for Sebastian as well.
Yeah. Thanks.
Yeah, what I understood from the chart is that we have an initial weight matrix that was this W, uppercase W, and what we are doing, the A times B matrix, is the delta W, and at the end, the final model would be the addition of those two ones. So W plus the delta W, which is what we train, what we fine tune. So at the end, this W is still there. The model, the base model is still there.
Yeah, we just made a tiny change on some of those.
Yeah, but that raises another problem, because the idea of fine-tuning, or the ideas of fine-tuning, are that you want, let's say, to specialize foundation model on a downstream task. Yeah. So you want to make a specialist, an expert in something. And on the other hand, you want to control the outcome of the new fine-tuned model in order to not to give you any, to avoid any hallucination or any stupid answers. So you want, the idea of fine-tuning is to take over the control of the output, which is how I understand it. Because if you have a base model which is pre-trained with rubbish data, then you will learn a lot of wrong things, and then you add your fine-tuning layer, but still, if the underlying foundation model, let's say, has a poor logic or a poor understanding of meaning, semantics, etc., how it could perform for your fine-tuning operation.
Yeah, I guess the difficulty is that when you have a foundational model, it knows some stuff from I don't know, the countries or the capitals of countries and stuff like that you might not care about, but it knows.
No. I care. I mean, I care about the not accuracy, but I care about the how correct is this pre-training process for the foundation. I mean, if the capital of Germany is Paris, then and everything goes along with the line, then well, you have a very bad foundation model, and you don't know it. Is the problem, and say, okay, I override with let's say poor behavior or poor training with my data set, and I perform this fine tuning using LoRa, and then this model will answer only to my questions for which I perform this fine tuning. I mean, that's why when I read Frozen, maybe I'm wrong, I don't know, but when I read Frozen, I say, okay, whatever you knew before, you forget about it, and you will know now what I teach you, fine tuning.
No, I think actually Frozen is the other thing. It's like the stuff that you already know, it will be kept like that, no changes. We're just gonna modify this other matrix, found the parameter, and adjust the base knowledge a little bit, like that. Salt up.
But again, if this is the case, we have there is an issue, because you don't make a full training, and this is the idea of cost savings, etc. So you make some assumptions that the model has already some information which is correct which is correct. Yeah. So this is your underlying assumption that model knows some stuff which is correct, and you fine tune it using LoRa or whatever with an additional data set for a specific down task. But if the underlying data or training process or pre-training is wrong, whatever sources which are used are not reliable, then well, the outcome will be wrong. I mean, it's common sense, in my opinion.
Yeah,
Yeah.
if that's your final task, if the knowledge that you need in your downstream task isn't captured in your initial training data, I believe, yeah, that would be the case. But I think what we typically do is like we think of those earlier layers as kind of the rudimentary knowledge in the model, like just natural language understanding and like facts about the world. And then the assumption is that the model can use those initial layers, which you keep frozen in your downstream task. Like when we did spam classification, the model knows how to like interpret language, so it can use those skills in the earlier layers to then do spam classification.
Yeah, I understand that, but again, the underlying assumption is that the pre-training was done with accurate data, which we don't know.
Yeah, that's true. It depends on what you're doing in your final task.
It doesn't matter the final task. I mean, in any case, your assumption is that the data used for pre-training is accurate.
Yeah, I guess when you fine tune, if let's imagine that you want to use Llama for something that is business related, and you are gonna need to trust, for instance, what I was saying, the countries of certain, the capitals of certain countries, because you want to make ask the model to make maps or something like that. Then I guess you are gonna have to basically start with tests of what you need. If your downstream task is create maps with this information, whatever you give it as an input, then you have to check for make tests for each of those countries, capitals, or cities, or whatever you need to the model to know that is right. Because otherwise the model is too big. I mean, models.
This is exactly how I did it. I mean, I download the Llama 318B. I ask a lot of questions for my future downstream task. It gave me rubbish back on bad things, and then I fine tune it with LoRa. I asked the same questions with a very good answer now this time. But still, when I ask who is Bon Jovi, I received answers, even though the fine tuning data was technical data. So I expect that I'm not receiving, let's say, answers from data outside of my fine tuned data set. The solution which I use some prompting and for anything outside my data, fine-tuned data, I said I prompt the model to tell I don't know. But by default, the model responds to anything he was pre-trained, which we don't know the source. This is the point of fine-tuning. You control the quality of the data, you make the fine-tuning, and this is what we want to avoid hallucination. Poor original data set used for fine-tuning for pre-training. So this is what you would make of fine-tuning. So maybe Sebastian can.
Yeah, I have not done this, but I have read that this is part of how people do fine-tuning. But maybe you can try to detect that something like you have to ask the model to see if the topic of the question is among the things that you want it to answer, and if it's not, train it to answer always something like "I'm sorry, but I cannot answer about things that are."
Yeah. So exactly. I mean, this is what I did. I mean, I fine-tuned Llama 318B with specialized data. I tested before and after the model to see how it behaves. And my expectation, maybe my wrong expectation, was that the model after fine-tuning will not be able to answer back to things like what is the capital of Paris or what for France or whatever, and then in order to avoid these answers, I use some prompting, and somehow I make a kind of steering of the behavior of the model to respond me only to the data or only from the domain I use the data to fine tune. So yeah, maybe my understanding was not, or the expectation was not
In
1,000.
case, I believe, in that case, I believe Michael would second me that that would require a preference alignment or maybe reinforcement learning. Like if
We cannot hear
you
you,
want
Taha. Can you say again? At least on my side, I was not able to hear you.
Yeah, it cut. But yeah,
model not to answer, like if you don't want the model to answer the what is the capital of France, all you have to do is you have to reinforcement you have to do a reinforcement learning on the model, maybe using the preference alignment techniques that we'll be studying later on.
Yeah, as I said, also with prompting, you can control this behavior using simple prompting, and the model will only answer from the data used for fine tuning. But again, I originated the questions from the what exactly means in practice. What exactly means in practice? The idea of freezing weights. This was my original question. But as I said, maybe Sebastian will help me to better understand what exactly are the implications of this freezing in practice. But anyway, thanks. So you can please go on, Taha.
Yeah, just another example. Is this image visible? Okay.
yes.
So if I show like I have so even if I tell it to maybe give a picture of a blue football, it will still continue to give me those pictures. Okay. Picture of while this model has already been fine-tuned onto a cartoon character dataset, it still remembers its pre-training. Like it does not forget what a football is or what some sort of architecture is. It will have its understanding of the previous pre-training. That is what we want to do. Like even when we fine-tune, the one thing that we have in mind that the model we are fine-tuning is good. It was trained on a good data. This is the first assumption
It's a good
of
example.
fine-tuning.
Sorry for interrupting, but this is a good example. So
Whenever we-
what you said is that the model still remembers, yeah. And you asked for a football, and you received another stuff. So this is exactly my concern, that the data which was used for pre-training is wrong or not accurate.
In that case, I believe, as discussed, maybe reinforcement learning rather than fine-tuning will help more. I believe Santiago will second on this.
Yeah, same. Yeah,
Okay,
and as
so
also as Eddie said, like, yeah, first step is prompting. If prompting is not good enough or doesn't solve all my issues, then yeah, maybe taking a look at reinforcement learning and human feedback. So you pass like this data set with the prompts, like the prompts to the model, and then a human actually runs the answers of the model, and then you train a reward model to so the model always answers in a way that the humans agrees. But of course, it will take a lot more time because in those cases, a human has to label the stuff. So yeah, I don't have any other suggestion apart from what they already tried and the complex reinforcement learning part.
oh, okay, cool. So moving forward, like what are the advantages of this process? Like it's more efficient, as already discussed. it is performance of models fine-tuned using LoRa is comparable to the performance of fully fine-tuned models, as we discussed earlier. What was the procedure of fine-tuning a model previously, which was a full fine-tune of updating the entire weights of the model, which obviously not everyone without a huge compute can do. So, and also LoRa does not add any inference latency because the adapter weights can be merged with the base model. Like this is what I was discussing, that you can keep the adapter weights separate and the base model separate. And what difference does it make is that we are not like adding some inference latency onto the model, and the model will continue to have the same, if not better latency as it was having when the time it was only pre-trained. So that's another plus point. So this diagram, as I explained earlier, we are adding two smaller rank matrices A and B rather than just having over here delta W. We have two matrices A and B, and obviously already discussed they have a certain rank, and that rank is way more smaller as compared to the original rank of the matrices that we have in our neural network. So these are a few utilities that we can use, and then over here they have discussed all of the parameters that from them I have already discussed a few important parameters. Then I would like to change over to this small notebook. Like it is still fine tuning because I have been fine tuning this Llama 3.1 on a data set that can allow it to do function calling. Like if you know what function calling it is a very important part of the agents that we'll be discussing later on. Like what agents are doing, they are most of the times calling different functions autonomously, and that makes them interact with different APIs and maybe different services on the go without any human intervention or a human need. So the base of the agents is function calling. So I was just trying to fine tune this basic Llama 3.1 model. Like a few libraries were installed here. I'm running this notebook on Runpod if someone is curious about it. And then I've just instantiated weights and biases. Weights and biases is a cool tool that can help you visualize the training of the overall fine-tune model that you're training. So over here you can see it has already improved the loss a lot, and it has been almost, I believe, 400 steps right now, and it's still in process of fine-tuning. So over here, I just added my API key and just loaded the variables for weights and biases. And weights and biases, as shown, can be a good tool in visualizing the fine-tuning job that we are doing. It is also a very good MLOps tool. I use it sometimes, but obviously the best is Nanny ML. So just moving forward. Uh, so yeah, so the next step I did was to load a face to access to a few wells, and I update model when fine tuning job is done. Then implement library. Practically speaking, it is like it's a startup, and they have been doing a good job in optimizing the tuning. It the whole of this tool is helps you find one.
I think, yeah, we're not understanding the last part. At least I couldn't hear. connection with Taha broke. Any questions? Well, he joins again, rejoins. Any comments? No. All right. Does anybody has like trouble joining Sebastian's AMA session? Does it collide like?
What is the question, Santiago?
No, if everybody can join the call with Sebastian.
I will join.
On
I
February.
will join. I will join.
Nice. Nice. Cool.
It's a good idea. Actually, I also thought about that. It might be cool to invite the author of the book in these meetings.
Yeah. Yes, from the beginning, he said that he would like to join when we finish the book, and but then he had an accident on a trip on Japan, I believe. So he then also told me like that he is having trouble like joining staff sessions and because of he was like he had some issues. But last week he said that he's feeling better. So if we would like to invite him, he's open to come. So yeah.
Let's hope he will not ask us questions.
Yeah,
What?
let's hope he doesn't test our knowledge.
we didn't get a test from Sebastian.
Yeah.
No, we'll ask the questions.
Yeah. Yeah.
While Taha is back, I want to ask you a question about fine tuning. Do you have some kind of rule of thumb or some kind of reference to decide when you are going to use fine tuning or when you want to use maybe RAG to improve a pre-existing model, or if it's the size of the information that you need the model to know, or if it's the type of task?
Yes, I experimented with stuff for a long time, last 2 years. So I think I can provide some small insights from my experience.
Go ahead.
Can you hear me? I don't know.
Yes.
Yeah. So I'll try to share my experience. I played with both RAG and fine tuning last year. So I accumulated some, let's say, some lessons. So RAG, there are a variety of RAG techniques you can use. There are sophisticated types of RAG, which I really liked, but there are some limitations to RAG by its way of operating. So there are some limitations to RAG for the use cases, even though the existing RAG techniques are very sophisticated nowadays. On the other hand, fine tuning, which I did for Llama 3.1 8B, is a new level, because you can, in theory, you can control the data you prepare for your data set. So say 1,000, 5,000 entries data set, and then you perform in 10 minutes to 20 minutes, you make a fine tuning for Llama. And then with a new fine-tune model, you can store it on Hugging Face on your account, and you can perform inferences as you want. So the best solution is the combination between these. In my opinion, the best solution is the combination between RAG and fine-tuning, plus agents. But it's another story. But there are a level of complementarity between RAG and fine-tuning, which makes the mix between both of them makes the best solution. For example, you can set your for a RAG system, you set, let's say, your data sources, which you select, which are reliable, and then the answers from your query will be extracted exclusively from your database, from your documents, and then these answers will go to your fine-tuned large language model and will be further refined. And then you get the final answer. And the final answer will have clear references from your database you use for your RAG. But the final answer is synthesized, is refined through your fine-tuned large language model. I think it's the best combination in my experience.
Yeah, indeed. I always heard, like, I haven't played that much with that, honestly, but I always read that the best is just to try both and combine them. That's
Maybe
Eddie
we can address a RAG session I can offer because I study with RAG techniques in depth in the last months and years, I would say, in the last 2 years at least. Yeah, to cover with RAG and especially the limitations of RAG. The limitations of RAG have a different nature from the limitations of fine-tuned large language models. Of course, everything has limitations, but they're different. They are different. So I can make a session with RAG if you want, and we can easily extrapolate, or we can, or even I can prepare, let's say, an overarching architecture for both RAG plus fine-tuned large language model if you want. I did it already, and so.
nice. Sounds cool, yeah. I'm on board.
So you can put me on the list in the next weeks, Santiago, and I'll prepare this presentation.
Good. I'll just take my about it. All right, I believe Taha is back.
Yeah, sorry. I'll just let me finish my notebook. It will just take 10 more minutes, and then Michael can continue with the DPO. Let's just share the screen. Okay, so I believe I was somewhere over here the time I left. So I was just mentioning Unsloth. Like it's a very good library for fine-tuning large language models. Like there are a few alternatives, like Hugging Face has TRL, and then we have this library known as Unsloth, and there is another library that I am forgetting its name. It's also related to fine tuning. Maybe it had its name related. Yeah, axolotl name is related to an animal. So most of these libraries are related to some animals like Unsloth. What they do is fast make the process of fine tuning faster. So a very unique name, Unsloth. Maybe they make it faster. So
did you test the performance differences between Unsloth and PEFT from Hugging Face? I use PEFT. That's why I'm asking. I use only PEFT. I didn't use Unsloth.
Personally, I didn't get a lot of improvement, but as per a few benchmarks, Unsloth is a lot faster as compared to normal Hugging Face PEFT.
Okay, and from performance point of view, I mean outcome performance, not speed.
No, like outcome is based mostly onto the fine-tuning data. That won't change. The library won't change the outcome of the fine-tune, I believe.
I don't know, but I think it might be an interesting exercise if somebody has this. I would have this curiosity to test these libraries against the same data set to see the differences, especially for the quality, not necessarily for the time, because the time might be relevant if library is 20, 30 minutes faster than another. So, but the quality is something you need to live forever with the output of the large language model. So maybe it might be an interesting exercise to be performed to compare these libraries against the same parameters, including dataset.
Yeah, we can do this maybe.
Yeah, might be interesting.
Yeah. So we have just loaded this Meta 3.18 billion instruct model that has already been fine-tuned on the instruction fine-tune method. Like it has already been fine-tuned. We have mostly two version of the model. models on Hugging Face. One is the base version, and the other is the one that has been already fine-tuned on the instruction data set. That the basic difference, like we have already seen, is that the base version will just continue to spit out tokens, and the instruct version will be able to talk to you in the form of chat format. Like it will be able to answer your questions, whereas the base version on the Hugging Face models will be just a token completion model. So that's the major difference between the instruct and the base model. And then we are using the token length of 2048. That might be the token length of the Llama 3.18 billion. This model, just loading the model, and it took a few minutes to load this model. And then what we are doing, as discussed previously, we are just giving a few parameters of the LoRa fine tuning. So as discussed, we are using the rank 16. It can be of higher values or lower values of maybe 8 or even 4, but I have not tested 4, but I have tested with values ranging from 8 to 32. And the higher you go, the more better training chances there are sometimes, but not in all cases. Like in flux fine tuning or SDXL, we usually keep this rank to 64 or 32. We do not go higher than that. But it also depends on the data set. The most important part that I would say in the fine tuning is the data set on which you are fine tuning the model. These parameters you can maybe change and test it out, but the most important part is setting the proper data and having that good data on which you want to fine tune the model. So the target modules I discussed already are the query metrics, the key metrics, the value metrics, and the output metrics that we have not discussed in the book, but it was implemented as I told GPT-3 onwards. And the LoRa Alpha, this is the scale on which the update will happen, as discussed previously. Update of the weights will happen. So if we increase the LoRa Alpha, the updates of the weight matrices will be more less normalized. They will be more the updates will be of, like, the gradient updates will be more as compared to the lower scale. And then we have the bias, and then we have the use gradient checkpoint pointing. It helps us to accumulate gradients and then updates after a few passes. Like it is more it helps in even speeding up the process, I would say. And then the same use rank sensitive LoRa, which is false, because in simpler tasks we usually do not require it, but you can test it to true, and maybe it might improve the fine tuning job. Then we are just loading the data set from Hugging Face, which is a data set made by Salesforce specifically for function calling, and just loading the data set and checking the length of the data set. And then this is an important part where we actually are using Unslot's chat templates, because when we are fine tuning, we want the data set on which we are fine tuning to be compatible with the training format, or the format that the model expects its data to be inputted inside. So over here we are just using the chat template by Unslot, where we are just keeping the format just like GPT, where we have a system role and the user and the assistant messages. So if I show you the data set, you will see here that we have 3 columns: the query, the answer, and the tools that the language model can call. So over here, we are just changing the data set into a format that will help us help the model to better understand the fine-tuning job. So that's what we are doing over here. And then we have a few parameters for the fine-tuning job. This is the batch size that we want. The higher batch size will require more compute size. So I believe this will correspond to the compute size that is available with us. Then there is gradient checkpointing or the gradient accumulation. That also, what we can do is after how many passes we want to update the gradients, that if it's 2, it will make the batch size even larger, and after maybe 2 passes we will be updating the weights and saving the weights after keeping the weights in memory for 1 pass, and will be updating after the second pass. And then we have the learning rate and the number of epochs, and maybe the precision points that we want to keep for the model. And then we have the optimizer over here, and this is the weight decay, maybe related to something regularization, but I'm not sure about this weight decay. And the next are the few parameters for weights and biases that we can load it there. And then finally, we have the our trainer that we are using from Hugging Face, and we are also loading the original model and the tokenizer for the model. And then we have the data set that is in the format that is discussed earlier. And then we are just starting the fine-tuning job. It's a very a small notebook, but it does all we need to do as the fine-tuning job is concerned. But the model is still training, so for demonstrating this model, I'll just update this notebook and maybe send it in the channel so that you can test the fine-tuned model out yourself. So I believe that's it today from my side. I can shift the podium to Michael so that he can tell us about DPO maybe.
Yeah, thanks, Taha. I do realize that we only have like 25 minutes left on our schedule time. So I'll start, but if we need to, just stop me, and then we can continue next week, or if you want me to keep going, I can do that too.
Yeah, let's do the 25 minutes and then continue next week, I would say.
Okay. Sounds good. All right, so I'm gonna share my desktop, and then I started with this notebook that is on Sebastian's GitHub repo, but I'm not going to go through his notebooks because I have my own one that I've added a couple of things to. But if you, I haven't pushed my, it's a private repo which I haven't open source. So if you wanted to follow along, you can go look at these notebooks. But I will start with my own notebooks here. So we're going to talk about DPO, which is this way to do preference training on language models. But before we actually start with the DPO training, I'm going to quickly talk about how we go about creating the data that we need to do this fine tuning. And this is another notebook that's also in Sebastian's repo that basically goes through this. So the form of the data that we need. So previously, when we did instruction tuning, we had data that kind of looked like this. So we had the instruction, we had an optional input and an output. So once we've instruction tuned this model, that's the point that you might want to look into preference training, and I'll talk about what that is in a second. But the shape of the data is slightly changed. So what you're working with here is, instead of instruction and just one output, you have an instruction and input. You have the actual output, but then you have these preference pairs. So you have a rejected and a chosen output. And the idea is that the preference pairs helps the model learn not just like what would be a correct output, but what would be a correct output that the user would prefer. So the way that you would typically go about gathering data like this is you would actually have the model, you present the same inputs to the model, to two different models, for instance. Let's say they have different seeds, and then you would give that data to users, like the two pairs of outputs, and tell them to rank them so they can choose which one is better. But this is quite a cumbersome and expensive process to have humans go through all of these outputs. So what we're doing in this notebook is we're going to use this technique of using a language model, like a much bigger language model than the one that we're training, to help us generate data that we can use for preference tuning. So we use a llama like we did in chapter 7. So I'm using the llama 3.170B model here. In the notebook that Sebastian has, he has some code to actually code to call the REST API of a llama, but I'm using a llama official llama client, which just makes it a little bit easier, so you don't have to write your own code. But basically, the way that you do that is by calling the API like this. And then here I was just testing it on my local machine, and I can send it a query to ask it what llamas eat. So we're going to use this local model to help us generate this data. But the input is our instruction data set, so the one that we used in chapter 7. So we load that in. And then we have this utility function that will format it in a sort of a small instruction format that we want the model to be able to use. So basically, it's just saying below is an instruction that describes the task, and then you kind of format it in that way, and then we can print it out. And then we have this code here that basically what it's doing is it's prompting the model for this, any input from our data set. We are choosing a random directive, so if the model should be polite or impolite, and then we're prompting it. So we give it this input that is formatted, and then we give it an output, and then we ask it to rewrite this output to be either more polite or less polite. So here's an example of how it does this. So the actual data set response would be, the spelling of the given phrase is incorrect. But since we prompted it to rewrite this output to be less polite, you'll see it's kind of rude to the user. And so we can use this code to basically loop through our whole data set. And that's what we're doing in here. And we are putting together something that looks like what I was showing you earlier. So this data set down here. And then I ran this on my computer locally. You can see it took a while, but I think it took like an hour and a half, but I was able to create this data set using a llama. So then I think we're ready to start using this data. Actually, let me just go back here. Go to my notebook. So now that we have the data set, we can actually start using it to do DPO fine tuning. So DPO it stands for direct preference optimization, and there's this paper that's pretty math heavy. So if you wanted to go through it, great. But basically, what this is doing is there's this idea of taking an instruction fine-tuned model. So we do pre-training first, and then we do instruction fine-tuning. But then what we want is not just for the model to be able to predict sort of correct outputs in terms of the instructions, but also add some other aspect to it. So for instance, it could be different things. So like here's an example where you might have a prompt, but you want the model to be either more or less technical, or you want it to be more or less user friendly. And these are the kinds of things that are sort of it's qualitative and it's not qualitative. Users are it's hard for someone to say assign a number to an output to say this is 9 out of 10 user friendly. So instead, what we're doing is we're using these rankings for the model to learn what the kinds of things are that users prefer. One of the ways that this was done before, and I think a lot of the big AI labs did, was to use this process called RLHF, which stands for reinforcement learning through human feedback. I'm not going to go through the whole process, but the key thing to understand is in RLHF, you have this policy model, which is the model that's the output of this whole process. So this model that's already been preference tuned. But the way you get this policy model is to first train this model that basically knows it's a reward model. It can do the same thing as the human rankers would do. So it'd be able to look at two outputs and an input and say which one it thinks is better. But this model is specialized for that task. And then you use this reward model to then train your policy model. With DPO, the nice thing about that is that you can skip that step. So instead of having this reward model, DPO directly takes your reference model, so the one that is already instruction tuned, and we keep fixed, and then you can train this policy model directly without this reward model to output with outputs that are more aligned with user preferences. And then the key thing when it comes to DPO, a lot of the fine-tuning works the same way as we've done before, but the one thing that's different is our loss function. And this DPO loss equation, it's quite meaty, and we'll go through it in a second. I'm not going to walk through it quite yet, but I just want you to kind of start getting used to it. What this is doing is it's basically a statistic. So this E is symbol here, E stands for the expected value, but you can just think of it as the average. And it's the average of our loss function that we calculate here when we draw a random triplet. So we have our X, which is our input, our YW, the preferred response, and the YL from this random distribution of our data set. And then I'll talk about what's going on here in a second. So we already talked about how we generated our data set. So here we're going to load it in. And then we just look at some of the data. We see it's in this format that we're already familiar with. And here's another example. So here we can see that it's, the model is root. So this is the rejected response. And then, the same thing over here. And then we have this utility function again to format our input, and an example of how we print that out. And then we also we can format our responses in this way. So we just add some like a template to that. And then like we did before, we split our training set into test, train, and validation. And so we're using 85% for training, 5% for validation, and the rest for our test data. So again, I'm going to kind of run through the next few cells pretty quickly because we've done all of this before. We're creating this preference data set, which is very similar to the instruction data set that we did last week. The only thing that's different here is that instead of returning a prompt and an output, we are returning basically these two different outputs, so our chosen and our rejected. And then we're also applying our prompt template that we implemented above. but the rest is the same. So we're just encoding it with our tokenizer. And then in the same way that we did last week as well, we have this custom correlation function. It's also very similar to what we have, but there are some slight differences. So we again we have we basically do call this function. We use this logic over here, but what we're also doing here is that we're doing padding in a slightly different way. So what we're doing is we're finding the for each of the rejected and chosen pairs, we're finding the longest sequence in that row, and we are masking based on that longer sequence. And the reason we're doing that is to make because DPO fine-tuning is quite resource intensive, that makes it run a lot faster. So what we had before is we did this on a batch level. So what we're doing here is on a row level, and I'll show you how that looks in a second. And then again, we can sort of pre-fill this custom correlation function like we did last week with sort of default parameters. One of the things that's also different is that we are masking our prompt tokens. So there's some logic here where we can mask out some of the format or the sort of prompt format tokens that we did before, because they're not really they're not contributing to our learning much. So we don't really want to, like, for each example, those will be the exact same tokens. So we don't want those tokens to or have to like account for them in our training. So we can see what this custom correlation function does. And here's an example of what it's doing. And then we will instantiate an example data set. So we can use our preference data set and a data loader with our custom correlation function. And we'll see it gives us the keys that we expect. So we have a prompt, chosen, rejected. I'll talk about these masks in a second. But when you look at each one of those values, you'll see that these are our tokenized strings. So we have the chosen one, and what you'll see here is that we do apply that padding, and that we'll only pad. So this would be the longest sequence in our row, and this one only has one end of string token, but here we have multiple because we're padding to the same length as this one. And then there's just some code to show if we decode it back, what does it look like? And this is what we'll see. And Sebastian notes here that like these end of text tokens will be ignored, so they won't affect our training outcome. Okay. So let's skip over some of this, but I will briefly talk about these masks. So the way that this works is this is how we're going to mask out our prompt token. So we don't want them to contribute to our training. So if we set this parameter to true in our custom correlation function, they will be masked out. Okay, again, just going to run through this. This is exactly the same as we did before. We have a data loader, so we have our train, our validation, and test data loaders. So what we can do is instantiate this train loader and run through it. And I think this is important to look at is, so here's the shape of our outputs. You'll see for each row, we'll have different lengths, but the length is the same on each row level. So that is basically padded to the same length as the longest sequence in that row. Okay, so now we can load in a fine-tuned LM to start our alignment. And fine-tuned here means our instruction fine-tuned model. So what we can do is we in chapter 7 we save the snapshot of that instruction model that we've trained, and we load those weights into a new model. So again, this is very similar to what we had before. We're using GPT-2 medium, and we're loading this instruction tuned model. And then we can prompt it, and it should give us output that looked very similar to what we did before. So we can still follow instructions like when we trained it last week. And then we're at this function that can extract the response for us, which we'll just use later. And then the important thing to remember is that we're going to be using two models. So we have our policy model and our reference model. At the beginning, they are actually exactly the same. So they have the same weights and they have the same architecture, but the weights are also initialized to be exactly the same. So that's what we're doing here. We're just setting this model that we loaded to be the policy model, and then we create this reference model. But it's important to remember the reference model isn't going to be trained or changed in any way. So just scroll down. Okay, so I think this is the most important part to kind of cover is this loss function. We have to kind of dig into it. Sebastian had some explanation here of briefly of what this function does, but it was helpful for me to kind of go through this symbol by symbol breakdown of what everything is. So I thought I could just kind of quickly talk about that. So we have X here. X is like one of the inputs from our data set, which is a prompt. And then our preference pairs are represented by YW and YL. And like I said before, so what we're doing is we're calculating the statistic, which is negated. But basically, this is the expected value or the average of this logged loss when we're drawing or when we sample a triplet of X, YW, and YL from the data set. Then we have pi theta, which is our policy model, and theta means the weights that we're going to be training. And then this is basically saying what is the log loss of pi theta when the output is x given output is y given x. So this can be thought of as a probability. So what's the probability of this output when we pass x into our policy model? And then we have the same thing for the reference model. And then the important thing is that we calculate these ratios of a logarithm. So what basically doing is here we have the logarithm of pi theta given our winning response our winning response given an x, and the same thing for our reference model. And then we do the same for our losing responses. And the big thing that you're trying to do in DPO is that you want this difference or you want to control what this difference is. But if the difference is big, then that's a good thing, because your the probability that you have that your policy model is giving the correct response is high, and the probability that it's giving you a low response is low. A wrong response is low. And then there's beta, which is this hyperparameter that you can play with. And basically what beta is doing is it kind of scales the effect of DPO. So the way that it's basically implemented in this equation is that if beta is high, then the model is penalized more strongly when it outputs are very different from the reference model. So if it's smaller, then you can let the model kind of drift more freely from the reference model, and then that can control sort of how much the model can stray from the reference model. So if you want to sort of amplify the effect of DPO training, you would set beta to be smaller. If you're a little bit more careful and you don't want to stray from the reference model too quickly, you'll make it larger. And then inside the parentheses, we take these logs of those ratios and we subtract them from each other to get that difference. And then we wrap all of this stuff in this logistic sigmoid function. Just to remind you, this is what the logistic curve kind of looks like. So what it's doing is it's taking those logs and it's basically turning it into a number between. Let me jump back. Oops. It's turning into a number between 0 and 1. So what that means is if the model is not performing really well, this value would kind of approach 1, and if it's doing really well, it would approach 0. And then we take the log of that, so that gets us back into the log space, and then we also negate that value so that we can turn this into a loss function, because when we minimize this negative value, then we're maximizing what's inside the expression because we want what's inside the expression to be big. So yeah, there's a lot to take in with this equation, and we can come back to it. I'm not sure if we should stop here. We're right at like time, but I'm also happy to keep going.
Yeah, I would say that this looks like a kind of natural stopping point. We review it next time, and then I guess you're gonna implement it in code is the next step.
Yeah. So
Like the code implementation.
we can implement basically what we just this equation here in code, and then we do training.
Yeah, I don't know how's everybody with time, but I think it should be better to stop and continue next week. Just do like every session 90 minutes. Does that sound right?
So, Michael, this seems to be like a good method for whenever you have two options, right? It's like either write a long answer and a short one, or but it's always for binary questions, right?
Yeah, you basically have you don't have a single number to qualify how like good an output is. You have just a ranking, so you just have like option A, option B, which one's better, and that's actually for humans, that's an easier task to do. It's you could look at two outputs and easily kind of say which one you prefer. Whereas like if you're ranking, if you have to assign a number, you'll see a lot more variation because what 9 out of 10 for one person might not be the same for someone else. So yeah, that's typically the kind of data that you want. But what is interesting is that you can use language models in a way to kind of gather or kind of create these artificial data sets that can simulate what humans would do.
Nice. And I guess the fact that it is like option A or B, like binary case, is why we don't need the reward model in DPO. right? Whereas in like a standard RLHF, you need a reward model that outputs like a score.
I believe in RLHF you're working with the same kind of data. It's just that with RLHF, I think DPO came after RLHF, so I think people just weren't aware that you can use that there is this way that you can train the model directly, get a language model, and I'm not enough of an expert to know why, but I believe that people use both. So I think RLHF is still being used, and I think for certain kinds of use cases, it still makes more sense. But DPO is used a lot because it's simpler. It's like there's less like hyperparameters, and the system itself is like simpler to kind of to tune and train. And it's more cost effective as well, because you don't have to train three models. You just have to do train one model directly.
Yeah, because the like what I've played with RL chat, I didn't train it by optimizing DPO. I did it by doing PPO, which is proximal policy optimization. I think it's came before DPO. And in that case, this instruction data set had not two options. It had like N options. It could have like
Oh, I see.
you prompt the model and you sample 5 answers. And then a human goes and say, okay, this answer is 5, which is the best. This other one is 4. This other one is 3. So it is more expensive, right? And giving ranks to a sentence is quite a difficult task. And then you have this reward model that is the one that is trained it is trained to learn how the human rewards, like how human ranks these sentences. So then the reward model can do the same job and get optimized by that. But DPO in fact sounds simpler. And
I believe
guess
it is.
that simplicity comes from the constraint that you only have to pick between two things, A and B.
Yeah. I mean, you can see from the loss function, it's kind of baked in. It doesn't really scale to more rankings. But I think for a lot of I would say that if you're just getting started with preference training, it's probably the simplest way to begin. And then like once you get to the point where that like you might have more ranking data, like the preference data is suitable for RLHF, or you have more reasons to kind of look at it. I think only then would you probably consider RLHF.
Cool. Yeah.
And one thing that's interesting is to like I was thinking about what Eddie was asking about earlier. And I think there's a good point there where you could maybe use a DPO or some kind of preference training, because for instance, if you don't want so the model is still retaining some of this knowledge, but if you're fine-tuning a model and you don't want it to, for instance, be able to to answer questions about unrelated questions, what you could maybe do is do this kind of preference tuning and give it examples of things where you wanted to refuse to answer. For instance, so if you're asking it about the Soccer World Cup, you can give it examples where the correct response is, "I'm sorry, I wasn't trained to answer questions about the Soccer World Cup," or something like that. So that could be a way of, because with instruction fine-tuning, if you think about it, you only give it positive examples. You're only showing it like, here's what I want you to do, but you're not telling it like what it shouldn't be doing. So this is a way to incorporate maybe some of that into your fine-tuning.
Yeah, indeed. Yeah, and that's also the case why in research this is called like the alignment task. Like you're aligning the model to answer in a way that you will like. But yeah, cool. So yeah, to summarize, next week we're gonna continue with Michael. Also, thanks a lot, Michael and Taha, for taking the time of the weekend and your own time and making this. It was great. I learned a lot. So yeah, Michael is gonna continue next week and finish with the DPO. And Eddie, also thank you. Eddie will teach us about RAC, an overview about RAC and his experiences with it. Cool. I have, let me share my screen. So I'll post this on the Discord so everybody knows the dates and the hour and everything. I will also probably like tweet about it so people that usually don't check the Discord is aware of it. And I'm gonna release this poll. I don't know if you guys have like more suggestions, but from the ones that I saw in the Discord channel, we have these 4 books: AI Engineering by Chip, Hands-on on Generative AI, LLM Engineer's Handbook, and this one that is actually the one that we can see here is Deep Learning with PyTorch, step by step. I'll give it 1 week of duration. I think I won't allow multiple answers, so because probably then if we allow multiple answers, every answer will have like 25% and it would be meaningless. So I'll allow only 1 answer. So yeah, pick the one that actually interested you the most, and feel free to like Google about the book, see the contents, and actually like see like so you can take an informative vote. I don't know, a vote with information. Yeah, that's it. That's everything I wanted to say before we log out. Yeah, thank you for joining and see you next week. Goodbye.
Thanks, everyone.
Thank you. Bye bye.